Start of the webinar, take 2. Hey, first off, thank you everyone for joining us for webinar number 1 of our 4-part series on reducing the environmental impact of roads through planning and design. I'm Erin. Hopefully you can hear me now, and I'm not just a talking head. I'm the Business Development Manager from Softree, and I'm going to be your host through the series. A little bit of housekeeping. I'm glad that so many of you figured out where that question and answer section is of your GoToWebinar panel. You can use that to ask questions. You can also use that to tell us if we have audio problems. So thank you. I will do a better job of monitoring that in the future. You can ask those questions, type them in anytime. We're going to address them all at the end. We have about 1 hour of planned content for the webinar series, plus the 5 minutes of extra time because it took us a couple minutes to get sorted here with the audio. So ask questions, we'll tackle them at the end. Okay, so moving ahead, hopefully you can still all hear me. Today is part 1 of 4, and we're going to be laying the foundation for the series. It's all about the impacts that roads have on the environment and a brief introduction to what geometric design is and how it can play a role in reducing that impact. So the content today, as well as in all the subsequent webinars, is not just applicable to forestry roads. It is applicable to all roads. So whether that is a mining access road or even an oil and gas corridor, the base concepts are applicable to any piece of linear infrastructure. And with that, I'd like to start my second attempt at an introduction with a little bit of background on why we are doing this series in the first place. So like most of you, the team here at Softree loves the outdoors, clean drinking water, fresh air, rivers that have fish in them. We also happen to create a geometric design software, which is usually marketed as a tool to help minimize your project costs and enhance planning. But it's also a great tool to help you minimize the environmental impact that a road can have. Now, there's a lot that can fit under that minimize environmental impact mantra. In fact, almost every decision that you are making during your road's planning, design, and construction is going to affect the way your road interacts with the environment and the impact that it's going to have. Now, some of these interactions may be expected and obvious, and others less so. And it also may be the case that you already know how you want to minimize your impact, but maybe you aren't sure how to account for it in your designs. So that's kind of why we've decided to put together this webinar series. Now, our goal in the series really is to discuss some of the common impacts that roads have on the environment, discuss some strategies to help mitigate those impacts, as well as ways that we can incorporate those strategies in our design and planning process. Now, we have the in-house expertise here at Softree to talk about the software specifics, but we thought it'd be really beneficial to partner with an industry expert to discuss the on-the-ground cause and effect side of things. And so for that, we're really excited to have partnered with On-Site Engineering for the development of this series. A very quick disclaimer too, yes, we do make the road design software RoadEng. We are thrilled if you decide to use our software. But our intent in this series is to be more informative than anything else. Our in-software demonstrations are going to be in RoadEng, but the base concepts really are universal. And even if you're not using our software, they're definitely worth considering. So today is all about laying that foundation, focusing on the impacts and considerations that you should be aware of, as well as what kind of role geometric design software can play in that process in helping you minimize those impacts. So with that, I would like to formally introduce our presenters, and we've got Jeremy Araki, our first presenter. He is one of the principals and founding members of On-Site Engineering. Jeremy has over 20 years of experience working in Western Canada, with his experience spanning initial planning, detailed design, permitting, construction tendering, inspections, as well as the assessment of older roads and infrastructure. Jeremy has helped to develop the engineers and geoscientists of British Columbia professional practice guidelines for crossing and professional development. And he has presented numerous courses on crossings and roads for associations, industry, and government clients. Next, we've got Matthew Dickey. He is From Softtree, he currently holds the title of Applications Engineer and Training Manager. His previous work experience has focused on the development of access infrastructure in both the forestry and in the mining sectors, and it has allowed him to add tremendous value in working with Softtree's clients and shaping the development of our software. Finally, although not a presenter, I would like to introduce Brian Chow. He has been a key contributor to the webinar series content and will be joining us and available for the question and answer section at the end of the webinar. Brian has worked for the BC Ministry of Forests for over 35 years and is currently responsible for the engineering standards and policies associated with forest roads and bridges that are referenced broadly as well as externally to the ministry. He has a keen interest in promoting knowledge and professional involvement for road engineering practices. So welcome, Brian, Jeremy, and Matt. And with that, I'm really excited to officially kick off the webinar series and pass it over to Jeremy.
I'm hoping that somebody can hear me now.
We can hear you. Hopefully you're off to a better start than I was.
It said it was disconnected there for a moment. Thanks for the intro, Aaron. Again, Jeremy Araki here. Sorry a bit for the background and my voice. I'm on day 5 of COVID, and so I might mute myself a few times to clear my throat, and I may remain still in a bit of the COVID fog. But nonetheless, here we go. I think just to add to what Aaron said in the intro, I think that probably the folks on this call and those we work with, we're in my mind, we're the best environmentalists in the world. And I say that because if you look at what environmentalism or environmentalists do, it's trying to manage and best protect our environment. And to me, the boots on the ground professionals and those who work in the industry who are doing their best to consider all the impacts that we have, manage for them, and really do our best job at being part of our environment. That's what we're doing, and that's the focus here today, to help to give tools to help folks to better consider those things. And like Aaron said, this is a 4-part series, so this is more of an introductory piece here. So we'll answer all the questions, but some of these ones you might have we'll be more fully developing as we go through. So I want to start with a quote by Benjamin Franklin. If you fail to plan, you are planning to fail. And in my career, I found that to be true most of the time. And really that's about time and money and project success. So there's lots of benefits of planning. It helps you identify issues up front, have time to consider them, to design solutions for them, and then schedule things so they come in the right time and timeline in your project, and then actually construct a successful project. Now, I said time in most of those things because that's what planning does for you. It buys you that time. But in my mind and in my experience, when you're talking about saving time and planning better, it almost always means that you're saving money, and that's really important. So as we go through this, we start talking about what are those impacts. So the impacts of the roads, the impacts roads have can pretty much be brought down to 3 kind of main topics, and that's water, which you'll see common throughout this theme, and along with water, of course, is gravity, and then geology and topography. Water finds its way into all of these things, everything and everywhere. It is the main influencer that we have. And the geology part, and of course it's powered by gravity. The geology part of that is the materials and the behaviors. So understanding what landforms you're getting into and their history can help you better understand how those things are going to react. So, and the topography obviously is the shape of the ground and how your road's going to interact with it. So, as an extreme example, we put a couple pictures in here, and the top one, clearly that's multiple phases as somebody was doing something on this land base, and they were not thinking about what they're going to do next. And that's not a common example. It's a bit extreme, but the concept is there. And then the bottom is the other side where there was clearly a design for this road, and not only was it constructed and trimmed all nicely, it's actually being survey staked and laid out, so you're getting exactly what you were expecting. And like Aaron said, I mean, we're showing a couple of pictures of resource roads here, but this is it's not only across industry, but it's across lineal infrastructure. It doesn't necessarily just apply to roads. So the other thing that I like to think about when we're talking about the environmental impacts and cost is when you have less impact, you're generally having less costs. And if you can think of that from the landscape level, like the smaller the area that your footprint is for your road or your structure, the less impact you're having on the environment, but also the less work you're doing. And so these things of considerations for the environment don't always contradict or go against profitability or productivity. So we talked about the impacts. The next piece is to talk about risk. And we hear that word all of the time, media and around, about risk management and so on. And I think a lot of folks don't really understand. So we're just going to spend a bit of time here defining risk. And what we have on our screen is the approach that we use here in BC. And it's consistent with Emergency BC and the best practices that we have through the associations. And risk is a formula. It's a likelihood of an occurrence times the consequence. And that likelihood of occurrence is just the chance of something happening, of a hazardous event happening. That hazardous event is anything that has the potential to harm, and that's health and safety, environment, damage to infrastructure, or any combination of those things. So that's the likelihood of the occurrence of that hazardous event times the consequence. And the consequence is the severity of that impact that event may have on whatever your element at risk is. And so that's in the right-hand side there, you can see higher major consequences or higher likelihood gives you a high risk. And so that's just a bit of background as we go through and talk about these things. So the next on the list is, what are those hazards? And like a lot of the things that we're going to do here today, these aren't exhaustive lists. These are just good examples. So hazards can come in many forms. The first one we have here is erosion, and that's just erosion of exposed soils or soils that have been mobilized. And that's generally from surface runoff water, but also from ditches and then into stream channels. And that can be from the increase of peak flows or redirection. And or we can just be talking about the erosion or degradation of sensitive soils, or an impact on a particular feature, and not just the impact of the transport by water. So sediment, the things that are being eroded, is that sediment and the delivery to a water courses. And that's not just accumulations in a water course. That can be accumulations in the road structures that we have. So in ditches or in culvert sumps, for example. So that's the sediment part. And of course, that feeds right into the debris flow or flood. And debris flows are basically, we're taking that sediment or increased peak flows and we're concentrating it generally into a channel or a gully. And what happens with sediment and debris when it gets in water is it makes the water heavy and erosive. So when we're talking about debris flows, we're talking about adding enough material into that water so it behaves as a really viscous liquid that has a lot of power. And so as these things go, they accumulate things and erode where water itself didn't erode before. And for the purposes of this seminar, the distinction between debris flows and floods is not really critical, but the flood part just acts still more like a, high flow that's carrying debris. So that's at the channel level. Sliding back to the landscape level, there landslides are another hazard, and that's everything from as small as an undercut slope from a cut slope in a road, or the overloading of a slope below the road. But it also can be from just changes in the water regime, and so we're talking about stuff right from the landscape level down to just small levels like a rockfall or a slump. And of course, that ties right into disturbed areas, where we're just talking about the overall disturbance to an area, where that can be related to soil moisture or temperature, or just disturbance to a sensitive area or element, or to productive land based. And of course, water flow. So we've been talking about debris and debris flows and that sort of thing. But when we divert or concentrate water, we can make other areas wetter and some areas drier. And we also, as soon as we divert those surface flows, we change the velocity, and we'll get into that a little later. But all of these things are going to alter peak flows. So the peak flow of any storm or river flow event. And whenever you change those peak flows, that's a hazard that influences the likelihood of all of those things that we just talked about above. And of course, as with those changes in water flow and the sediment that we talked about above, that can and will alter stream characteristics. And that's how the stream behaves. So that's everything from the shape of the flow or the shape of the channel to the movement of bed loads. So, erosion of banks, changes in movement of bed load. And just as a quick example, on the picture on the right there, you can see there's a number of landslides, but if you kind of look left to right there, you can see the first long skinny one, that's a fill slope related slide. There's another little one right beside it, and that's something up in the cut block and open slope thing. The next one, it looks like it's a cut slope failure that got down across the road, and then probably a wind throw failure above the road going down through, and then on the very far right there, it looks like another cut slope failure, but that could be something retrogressing as well. Anyways, that's on the hazard side. Next to the consequences, so elemental risks and the consequences on those. And again, this is not an exhaustive list, but we're just trying to provide some context here. And of course, there's a long list of animals, not just the ones that we think about off the start. We put a salmon and an elk up there, but everything from invertebrates, reptiles, birds, and everything in between. And it's not just the first order impacts that we have to think about. For example, in the north of North America, there's studies that show increased predation of wolves on animals, and that's not just ungulates or large animals will travel along plowed roads in the winter because it's an easy way to travel. Then they'll have snowbanks they have trouble getting off of, so that kind of funnels the animals for wolves to predate. But also wolves are smart, and some of the seismic lines up north, they've shown that the wolves are using them as kind of grid lines to cover large areas and cut off their prey just by using those lines. And so it's not just first order impacts. So the other part of it is on the fish side. You think of stream hydraulics and how that impacts fish and spawning. So when you alter peak flows, you're going to alter how that bed load behaves. And so that's from the amount of it, where it is, and its gradation. So, different species of fish need different types of gravel or sizes of gravel to spawn in. If all of a sudden you add, for example, more fine-grained materials in there, then you're going to change the ability for those fish to spawn. So from that small level down to the landscape level of fragmentation of habitat, like we were talking about with the wolves up north, and the overall movement of that wildlife. And then on the non-wildlife side, you know, the introduction of non-native species along the road. Here on Vancouver Island, we have Scotch broom that you can see gets pulled along roads all over, and it's an invasive species that's quite damaging. So those are the things right at it, but the other downslope elements at risk from our perspective is, you know, transportation utility corridors, water intakes, land-based features like productive land base, protected areas, ecosystems, and other features important such as arc features. The picture on the right is one of my favorites, has an old colleague in it, and this is a test hole in an ancient cedar from the Native North Americans here, First Nations, where they would cut into a tree to test it to see if it was appropriate for the building materials. So, you know, protecting things from, you know, a single tree to the landscape is things that we need to consider. Sorry, I'm just gonna have a drink here. So one of the most important things I think we want to get across today as we're thinking about these impacts is not just point in time impacts of a road, but impacts through the road's life cycle and making sure our roads are sustainable. So starting off, what does that mean? What does sustainability mean? Well, I'm an engineer in British Columbia, so I use EGBC's definition. So I'm just going to read it to you just for context. So EGBC says for sustainability, a sustainable society meets the needs of the people in a resilient economy without compromising the planet's ecological integrity or the needs of future generations. Sustainability has three pillars that must be integrated in a balanced way. One, environmental, to stay within the biophysical carrying capacity of our region, country, and planet. For example, minimizing resource use, minimizing waste, and protecting nature from degradation. Two, social, to maintain and protect quality of life and the values that we aspire to live by. And three, economic, to ensure that an adequate material standard of living is provided for all members of society. So that's what we say is sustainable. So the question is does or will your road perform as intended through the entire lifespan? Will it do its job? Are each of the areas of impact being managed at each life cycle phase? If it's a short-term road, does your plan take it back to as close to original as possible? If it's permanent, does your plan manage for the least risk all elements at risk through that life cycle? And how have you considered it through its lifespan? You know, and you have to consider all phases in particular for the next one. So in the planning phase, you need to be thinking then about what the impacts on maintenance will be of your plan. So that's sustainability and life cycle. And really, you know, in the circle there up on the screen, we're talking about the kind of the preempt to this of impacts and considerations, but that's the input to planning. And it's really important to distinguish planning from design. We get an overall plan, then we get into design, and then construction, use and maintenance, and deactivation. And a lot of times, I think that use and maintenance and deactivation is not considered properly upfront at the design stage. Sorry. So again, this is a 4-part series. And this is an overview of planning considerations, and the rest of the series is going to be focused on the how-tos or not-tos of this planning and design. And sorry, excuse me, my voice is starting to get bad. So I'll dig into the details as we get into this on the technical side. That's what I'm here for. And then Matt Dickey will get into the software side of how RoadEng can help. But at the base of everything here, as I said at the start, water impacts everything. And it is, I don't want to say the basis of all evil, but the basis of all damage and change comes from water, and it's everywhere. So we're going to get into that a little bit because it's one of the bigger considerations we have. So let's start with an example of just a normal hill slope. In our example here, we have a forested slope. And water, everything on about a slope will impact it, from the slope of it to the cover to the ground cover underneath. So when it starts to rain, water falls on the slope and it starts flowing down the hill. So as it's flowing down the hill, so you can hopefully see in the graphic here, water on the surface travels a lot faster, and it's going to be impacted by things like I said, slope, the forest cover, and the ground cover. Like you can see, it'll slow down in the, you know, in the heavily vegetated areas. But as it's flowing down the slope, it's also infiltrating. And that infiltration is really important because it slows the water down. And we're not even talking about the uptake in the vegetation right now, just how it flows down the hill. So as that water flows in, it slows down, and it can slow down orders of magnitude in velocity. So it's traveling through that slow soil profile. So it's not only changing the speed, but it's changing how fast it's getting down the hill, because it's got to go, the path is not straight anymore. Also, as it travels down the slope profile, we can have features in the slope profile, such as bedrock surface or a glacial till or a fine grained soil that will act as an aquiclude and concentrate water through the soil profile. In any case, over time, slopes develop with the ability to handle these peak flows and this flow pattern. As soon as we cut into that slope, we are going to interrupt that, full stop. There will always be an impact on water when you build a road. So as we cut through that soil profile, you can see the water is going to be coming down the surface. Even the surface water speed, as it comes off of the forest floor onto a cut slope, it's changing its velocity. It's even more dramatic for that subsurface flow that we're catching that's emerging from the cut slope, flowing down it, and either concentrating in the ditch or flowing over the road and down. So now we've intercepted that water. We're accumulating it because it's changing its velocity, and then we can redirect it up and down or across the hill slope as it flows down the road or flows in the ditch. So the important thing to remember, as I said at the start, is that these things will always happen no matter what you do when you're building a road. And so the three concepts that are going to be, again, throughout here is the interception of that water. So we're intercepting it out of the cut slope or with our road structure. We're accumulating it because we're changing the velocity, and we can redirect it. So that's along the road. So those three things and those three concepts are important to consider because we know they're happening. We want to do our best to manage for minimizing them where it matters. So that's at the cross-section level. As we look back to the landscape level, this is just a typical DEM of a slope. And as it rains, water comes down, hits the slope, and it hits the ground, and it starts to infiltrate and disperse. So these are just flow lines that are draped over the tin. But this water is now going to start concentrating into the channels as it flows down the slope. So as it's concentrating in those channels, those get bigger and bigger as they go down the slope. And like I said before, those are developed over time to handle the flows, the peak flows that they're used to. And that impacts everything from the channel that is formed to the vegetation that's either around that channel or on the hill slope across the landscape. So again, every time that we build a road, we impact that. So in this next example, that same hill slope, we build a road up. And this is typical the kind of road scenario for us on the west coast of North America, where we have steeper ground. And we're climbing up from the bottom of the stream there with our road, following the contour. And then we have to change directions. Well, where we change direction, we call that a switchback here, where we want to change those directions on the flattest spot that we can find on the hillside. And almost always that is on a ridge, and the ridge is often between two water courses. So we change directions on that ridge and keep heading up the hill. Now when it rains, the water comes down the hillside and it hits our road. So that's not just in the in the drainage courses, like I said, that's that surface and subsurface flow all along that cut slope. And so in this case, as our road climbs up, we're intercepting all of that drainage. And if it's flowing down the road or in the ditch, it'll flow to a point where until it can get off. Well, in this case, and like I said, if you look back at the history of landslides in coastal British Columbia anyways, this is a super common reason for landslides. That water flows off the end of the switchback. And so not only have we changed that accumulation and concentration of flow and redirected it, we've redirected it into a drainage path that has not seen those flows before. So even if we just increased the flow in that channel, it would be bad. But now we've increased it by putting different channels. So it's not just the impact on that channel, it's the impact on the hillside that's below our road, where now there's no water flowing. So it's important to mention here, I should have said this earlier, that I'm giving you a steep slope example, but this changing of water regimes happens on every landscape, and especially in fine grained soils. Some of our flatter land in Canada and the US, we have a lot of fine grained soils, and just slight changes in soil moisture or cuts into those slopes or gentle gradients can have pretty significant impacts on the stability of those areas. So, and then on the channel side, in streams, changing of peak flows and sediment load, those impacts are felt across all channel gradients and all ground types, from slow meandering rivers to steep, short mountain streams. So these things apply across a wide variety of areas. We're just giving this one steep slope example because this is where I work. So the next slide is us, managing water. And, like I said, we're going to intercept that surface and shallow subsurface flows. But what we want to do is we want to add drainage structures, not just in the drainage paths, but in the areas between where we know we're going to be intercepting and accumulating flows just because of our road structure. And now, as you can see, we've at least kept the water in the general drainage basin where it was started. We have still changed the velocities. So regardless of trying to minimize redirection, we're still intercepting and accumulating. So it's always going to happen. And you're actually always going to redirect. We try to mimic natural drainage patterns, but as you can see, in between these culverts and below the road, we're going to starve some of those areas of water, and we're going to increase flows in the channels higher up than they would have been before we built our road. And this is not just the distribution of water impacting the landscape and channels. With those come changes in sediment, which is the next piece of our puzzle here, is how we manage that sediment. And remembering, again, those same three comments, the concepts of interception, accumulation, and redirection. But because we need to manage for sediment, we have to think about this. And we've got, in the fourth seminar, I think, we'll talk a bit more about the structures of that. But in general terms, all forest roads or resource roads and crossings are sources of sediment. They all are. And what we want to do is locate roads and our associated crossings and design and construct them and maintain them, recognizing that they are a source of sediment and they will have an impact, and locate them to minimize those, especially on water quality and fish streams and fish habitat. But the considerations for management of sediment should be made not just for construction, but through the life cycle of the forest road and the crossings. For example, sediment sources can change over time. In an initial construction, you have a lot of open slopes. You've opened up a lot of new faces, so you have big sources of sediment from cuts and ditches. But over time, those things will vegetate and stabilize. but the road surface will deteriorate, and with higher use, you'll have more sediment coming from the road surface itself. And then on crossings, well, that's a whole, we could do a seminar just on sediment delivery from crossings. That can change over time, and it really depends on maintenance. So those are all things that we need to think about. And they can be, and like I said, we'll get into it later, they can be dealt with in a pretty significant way just from planning and design. And in my experience, and it's not always true, but it's generally true, it's cheaper to deal with these things up front rather than to deal with them in a reactive manner. Because remember, water is power, water and gravity is power, and no matter what kind of structure we build and how grand we think it is, it can get taken out. And rather than rebuilding a structure, sometimes that little thing that you can fix at the start will avoid all that. You know, there's a bit of an extreme example of fine-grained soils in the background of this slide, but you know, slight slope on here with a new road surface, and if you let this go, as soon as water starts to dig a channel, it's just going to get worse and worse, and pretty soon you're going to be rebuilding. So in any case, we want to plan all activities to minimize the potential for sediment, and that's the sediment development. So where were these sediment sources and how it's moving. And generally, the easiest way to do that is to try to best mimic the natural or pre-existing drainage patterns. Oh, how are we doing for time? Doing all right. So we've gotten into a bit of the details here. The next step is going to be talking about how that team is put together, and really that's everything from specialists to stakeholders, that, you know, government, communities, First Nations, the users, to the planners, the engineers and techs, me, but not to minimize that role of the road builders and the maintainers and the contractors, because that's where the rubber meets the road. So we've had a lot of advancements in the last little while, even from the survey and equipment side and data collection. We have LiDAR now, and we have this onset of GIS, which is a huge help in planning. And then we have geometric design software. And I think that's the end of my expertise, and we'll let Matt get into the details of RoadEdge.
All right. Well, thanks, Jeremy. Yeah, so I'm going to pick up where Jeremy left off here, and I'm going to reiterate some of the concepts that Jeremy touched upon. They're important. This is our introductory webinar, so yeah, I won't try and repeat everything, but you will hear some stuff that's familiar. My goal here is I'm going to go over an overview of geometric design software and discuss a typical workflow. So that being said, I'm not going to jump right into the details of some corner of the software and show how we can account for one aspect of the designing around the environment. My goal here is to just give a foundation to expand on later. So we're going to cover a basic workflow. We'll touch on a few broad points, but we'll definitely get more detail oriented in our later episodes. So to start, what is geometric road design? So it is a matter of incorporating your topo survey information with your design standards to create a model that balances a bunch of conflicting values. So we want to maximize the usefulness of your road. You're building a road for a reason. We want to minimize the costs. We want to minimize maintenance requirements. We want to minimize safety concerns. And we want to minimize those environmental impacts. And if you look at any of these in isolation of one another, you'll probably end up with an impractical solution. So you'll evaluate all these things simultaneously, and you'll also figure out your horizontal and vertical alignment, cross-section geometry, road drainage plan, and earthworks requirements. And these road components are interconnected as well. So if you move your horizontal, it's probably going to affect your earthworks, and then you're probably going to want to change your vertical alignment. So and that kind of snowball. So it's all this big interconnected balancing act. So that big balancing act can be done without computers. It's just really hard and time consuming to consider everything in a cost effective way. So design does take time. If you're going to do this all by hand, imagine how much fairly simple but time consuming math goes into it. So figuring out things like curves, volumes, disturbance areas, illustrating scaled views at the right location, etc. So without geometric design software, you either end up spending an enormous amount of time or you end up grossly simplifying the problem. So at a basic level, the biggest benefit of a software is we can automate a lot of the modeling and background calculations to streamline solving the problem without having to oversimplify it. So design software makes it as easy as it can be to do geometric design. Now, usually design software is not going to be the only software tool in your toolbox. So GIS and design software both have their place in a project life and fill different roles. So they aren't the same thing, they do different things. GIS is more a landscape level tool to store, manage, and analyze spatial data. So this analysis is geared towards points, polylines, polygons, raster data, and the analysis can handle an enormous amount of information, but it's less interactive. Now, design software is more of a tool for local analysis and is set up to easily account for design constraints and evaluate your project as an alignment and separate surfaces. So an alignment versus a polyline, an alignment has curves in it. And instead of considering the road as just a line, it's going to be a surface. So we're going to look at how your road surface, so not just your running surface, but cut slope, stitches, etc., how that interacts with the surrounding terrain. So it's more detail oriented and it's more interactive. And if we just look at the example that's shown here, if we evaluate this road based on the image to the left, it doesn't look too bad. Now, if we look at that in a design software, yikes. And that's not to take away from what is done right here. There's lots that is done right. If we look at the actual details of it, it looks like their grades work. They're in full bench construction where they should be in full bench construction, and they come around their switchbacks and they daylight out to minimize as much as that cut as they can. But without a design software, we don't see exactly how much work is involved in this. So there's an enormous amount of material to move, and then we can look at the other complexities that we create here. So we've got roads right on top of cut slopes, which it may be doable, but you're probably going to have to reinforce your soil or rock if you have that going on. So oftentimes it's a case of, well, this is a lot of work. Well, at least we can plan for it, or this is a lot of work, let's find a different way to do it, or this is too much work, let's just abandon this and not pursue it any further. So the value of doing a road design stems from the fact that you consider more quickly. So for those that do not do geometric design, there's a common belief that adding design into their workflow will be time consuming and add just another cost to a cost sensitive operation. So with a few exceptions, especially with LiDAR, this is a misconception. So the design process is quick and the cost for someone to put together a quality design is outweighed by their benefits. And no manager likes bad surprises. So designing and reiterating a bunch of the stuff Jeremy introduced, designing in advance of construction gives you an opportunity to avoid those surprises. So broadly, designing can help you better evaluate your options qualitatively and quantifiably. So this includes our 3D visualization of the proposed works, also tabular outputs. Helps us avoid costly and challenging obstacles. It helps us account for project challenges and complexities to help determine project feasibility, improve planning, and improve scheduling. So that whole case of at least knowing what you're up against to make sure you have the right tools and materials on site when you need them. And it's a great tool to create project documentation, to communicate and record project expectations. And as we'll elaborate on as we go here, it's a great tool to reduce environmental impact. So as a testament to that first quantifiable approach note, it is valuable and it is tangible. So if you just look at the two images down below here, they're similar in length, a few hundred meters long, on the same relatively benign ground. And one of these requires about 80 truckloads more of material to be moved along it. And you may say, well, I can just look at that and know that if I contour around the slope, it's going to take less material. It's a benign example, but just imagine if it was more pronounced. It's a question, well, can I actually get around that slope and keep my design standards as I like? So is it going to be safe to drive on? If I go from having that through cut on the straight road to daylighting it out to minimize some of my cut, is that cut slope going to extend down somewhere where it shouldn't be? So it's all about that whole giving you a better picture of what's going on and an idea of what you're up against and planning around those challenges as you encounter them. So regardless if someone formally designs your road or not, someone must figure out where and how to build your road. So that can be a designer and or it can be the equipment operator. So without a design or with a poor design, your equipment operator is effectively doing the design. So instead of being able to click in a bunch of options and weigh the pros and cons of each before selecting the best solution, the operator is likely only considering as far ahead as they can see, and they may not be aware of all project requirements and environmental considerations. Furthermore, when they're unsure of something, they're stopping production. When they're indecisive, they're going slow. So usually we aren't talking about slowing down just one machine, we're talking about slowing down a crew of machines, burning diesel with high hourly costs. Now, as just a digital model on your computer, the value of your design likely hasn't been maximized. So it may help you know where you want to put the road and how you want to build it, but you are probably not building it. So to maximize its utility, it needs to be communicated in some way to an intended audience. So common audiences include clients, project owners, regulatory bodies, and most importantly, those folks that are actually making what you've designed work. Now, for this, there's no one size fits all for the best way to communicate your design. It's important to know your audience and tailor your method and document to suit. So following our 4-part series, we plan to have a webinar focusing just on communicating your design. And that's intentional. It's basically our part 5 of our 4-part series. So it's meant to be meant to complement this series. Now, I've just said how easy it is to use geometric design software to design your roads, but there's no consider everything or do it for me button. So ultimately, it's up to the user to recognize the impact that their design will have. So in line with that, the more you consider, the better your design will be and the more robust your plan will be, creating value for your project. Furthermore, the more complex the project, the more valuable design is to it. So to maximize that value, it's important to recognize that there are design and model limitations. So it is impossible to eliminate all assumptions, risk, and approximations. Our goal is to reduce them. So as a first step, I'd recommend don't think of geometric design software as a black box. It's a tool to create a model, and the model is a product of your actions and inputs. So take some time to familiarize yourself with it and how things work. It can be very simple or very complex. Usually, the most common and influential design assumptions and approximations relate to topo data and geotechnical information. So geotechnical information, I'm just referring to what's underground. So nobody has X-ray vision, and often detailed geotechnical investigations are cost prohibitive. So usually if we're building a new road, we don't have good access to get in somewhere. So it's hard to get equipment in there, and hand-dug test pits take time and effort to dig. So nobody has X-ray vision. We don't always do the geotechnical investigations. So there's a lot of uncertainty about what's underground. Even with the detailed geotechnical investigation, sometimes you may just get unlucky and you have different conditions immediately outside your test pit. So if we look at this example, if you're able to ignore the cut slope in the built road there, if you can imagine just walking along the hillside before a road was constructed. To me, it looks pretty homogeneous, not a lot to indicate that there's anything going on out of the ordinary. Of course, sometimes you get unlucky. So here you can see it was excavated, and just below the surface, there's a short bedrock wedge. So it's one of those things. Plan to change your plan. It doesn't always happen, and local knowledge is a valuable tool, and a little bit of geological knowledge goes a long ways. But sometimes you get unlucky, and it's just important to have an open dialogue with your builders to make sure things can be adjusted as needed if need be. Now, on the flip side of that, we've got our topo data. So we love LiDAR data. It provides a lot of advantages over other data types. But as we can see here, it's not all created equal. So you shouldn't blindly assume it's a perfect representation of what's on the ground. If we look at the image to the right, that I assume there's a crossing in the low point there in that corner. The slope going down to the crossing looks relatively benign, where if we look at the one on the left, it's obviously a pretty steep bank. So this, if you're looking at a landscape level, this is just a detail that could go unnoticed. But if you're actually designing through here, if you're trying to widen that road, for example, it may be the case that if you blindly rely on the photo or the surface on the right, you may think, oh, I can just fill down onto that benign slope and don't have to worry about it. Well, if you look at the photo on the left, that surface is very steep, and maybe you have to push further into that high cut slope in order to avoid a negative interaction with the stream. So as we've acknowledged that there's limitations, it makes sense to consider those limitations as you design. So ask yourself, what if variable X isn't reliable or I made a wrong assumption? Will it make this project infeasible, cause environmental damage, or cause cost overruns during construction? If so, is it manageable? Can I reduce the risk with additional field investigations and design revisions? What are the requirements for construction monitoring, supervision during construction, etc.? So I'm almost done talking, or well, I'm almost done talking without any software stuff showing. So we've put together a quick video to go over the main concepts of a basic workflow. Now, for the sake of timeliness, we aren't going to cover everything at a click-by-click level. If you need or would like a click-by-click example of a basic workflow in our software, I encourage you to check out our YouTube channel. We have lots of examples on there. The example I've chosen today is a fictional resource road project. It contains watercourse crossings, a steep terrace, and a flat plateau. So since it's a combination of steep and flat, it should have content applicable for everyone regardless of their geography. When we get into the software, we're going to go through an 8-step workflow. So this is usually an appropriate and fairly efficient sequence to follow, but it's not set in stone and it is iterative. So step 1, we're going to bring in our topo data and create a model from that surface. So we're going to create a tin. Now, as a note here, the example I've chosen is LiDAR data. And the content that we're going to cover is applicable for other data types, but the workflow changes if you're using conventional survey data. And that is that LiDAR data is great, conventional survey data is great, but oftentimes you don't know where to put your road when you first start out. So with that, you have to go do a bunch of field work, a lot of walking around, and select a route to pursue. So that's, you're figuring out your preliminary alignment is your P line, then you survey it, and you're usually only getting a set width for survey data. And then when you come back into the software to really refine the plan, you're limited to your road to sitting on that surface that you've surveyed. Now you can always go back out and get more survey data, but it's not the same workflow whether if you have large LiDAR data sets where you've got a landscape to play around with. You can start at a fairly detailed design level before even going to the field. And usually it changes your approach when you go to the field from where should I put this road to is there any reason I shouldn't put this road here, or is there any data I can collect to make my design better. So then we'll take that LiDAR, or we'll take our topo data, make a model out of it, and then we're going to jump over to the actual design side of the software. And for that, we're going to start by setting up a cross-section template. We're going to select our horizontal alignment, and as we do that, it's going to become iterative as we adjust our vertical alignment, add curves, etc. So there's lots of refining. So step 4 is our vertical, and then we're going to add crossings and drainage structures. Now this is adding it in there is more appropriate for your minor crossings. If it's a major crossing, oftentimes your major crossings are going to dictate where to put the road, so it makes sense to figure that out first and then get your road to those crossing sites. Now, once we've got our design nailed down and we're happy with it, we're not going to just blindly assume that we've nailed it, especially if it's just based off a desktop investigation. We'll go to the field, we'll field truth it and make sure everything makes sense. If necessary, we'll make revisions and then we'll build it. So with that, we're going to jump into our video, and I am going to go probably 15 minutes over here. Sorry, guys. But yeah, we'll jump into our video and we'll cover our workflow. So we're going to start by bringing in our data. So for this example, I'm not going to start right with my LiDAR data. I want something to give me an idea of what's going on in the project aside from just the surface. So I've brought in an AOI, area of interest. I'll bring in an ortho photo. And then here, I'm just going to bring in a single shapefile. In this case, it's going to represent where I'd like to get my road to. So I'm going to use it as a resource road example that's going to a cut block. Next, I'm going to dump in my LiDAR data. So that's survey data. And that survey data is going to come in as a big cluster of points. Now, that survey data is not yet a surface. So we'll take that cluster of points and we'll model our tin. And when we model the tin, we're also going to create contours. So the contours themselves are just an illustration. What's going to really drive the design is the surface. We're not going to blindly rely on the contours, just most softwares will, including ours, there's settings in there to allow you to thin and smooth the contours so they look better. So we can take some details away from it. And then also, if you have any information that land between your contour intervals, you don't get to see those details. So when it comes time for us to check the surface, we're going to use our 3D view. And when I'm checking that, I'm going to start out just kind of at a landscape level, look for any obvious issues. I'm also going to start to look for any landscape features that may give me an indication of hazards or what geotechnical conditions to expect. And I'm going to begin to piece together where I might have an opportunity to get a road. Once I'm happy with that landscape level, I'm going to zoom in and look at my critical areas. And again, I'm going to just keep evaluating, okay, does this surface look reasonable? Should I check it out with closer detail when it comes time to field truthing? And for critical areas, I'm going to include things like intersections, crossings, switchback locations, and any steep, complex terrain. And if you're in flatter terrain, it'll be looking at ridge tops or low points where you expect to place that road. So once we've got our surface and we're happy with that, we're going to move over to the design side of things. And in our software, that's switching modules and opening up location. So we'll save that, open location. And the first actual design consideration that I'm going to make here is make sure that the cross-section geometry I'm using represents what I'd like for my project. So in our software, that's in our template editor. And I'm going to just make sure the dimensions and behavior suit what I'd like. So in this case, we're going to keep it simple, just go with our default cross-section geometry. But we can account for a lot with these. We can have a lot of complexity and logic built into them, and we can assign different cross-sections along different sections of the road. But we'll cover some of that stuff later on. So once we've got the template that we'd like, I'm going to start figuring out my horizontal alignment. And as I do this, I'm setting my horizontal alignment in my plan view, that bird's eye view, but I'm paying attention to what's going on in the other views. So I've got my 3D view down below. I've got my profile to the left, and that's showing what the ground's doing underneath the road that I've clicked in. Now, as a first step, and everyone's got different personal preferences for how they approach these things, but I'll usually do my roads in little segments, and I'll try and nail them down as best I can as I go. But I'll start with the horizontal, then I'm going to start adding the vertical. And as I add my vertical alignment, I'll take into account my cuts and fills, pay attention to my cut slope, fill slope, etc. And I'll probably have to adjust the horizontal as well. If it's any kind of terrain with any kind of complexity to it, it's wiggling around to find that best place. Now, as designed so far, it'd be very uncomfortable to drive on. I've got some pretty abrupt corners. It wouldn't be safe. So I'd add curves to it. So again, I'm going to start with my horizontal and I'll add horizontal curves. Again, I'm probably not going to nail exactly what curve to apply where. I'll make adjustments, move them around to change my the radius of those curves. And then I'll go over and do the same for my vertical curves. Now, usually for me, when it gets to the level where I'm adding vertical curves, I'm paying more attention than just the geometry of the roadway itself. So I am still paying attention to that, but I'm also starting to pay attention to my earthworks. So for that, I've got that little graph in the bottom left, which is our mass haul diagram, and that's tracking our surplus and deficit of material. So if we are going through a cut, we're creating more cut than fill, we're creating a surplus. If we're going through a section with more fill than cut, we're creating a deficit. So we want to take that material and we want to know where it's coming from and where it's going to. So we're going to balance our alignment. We're going to pay attention to the direction. So right now, as that's designed, I've got mass haul going up above the zero line. So that up above the zero line material is assumed to go forward, which I don't want. In this case, I'm on the steep side slope trying to ramp up to get on top of that terrace. It's not reasonable to expect a truck to move that before there's a road there. So I want to make sure that that material is going to head backwards. And I can add some graphics here to see what's going on for that mass haul material movement. And in this case, with that balance that I'm doing, it makes sense. We have to go through a steep section. It's going to be full bench. That is what it is. But right before that, I've got a switchback, a nice broad switchback. But I can use the cut material from that as a fill to help minimize my grades. Now, once I'm largely happy with where things are at, I'm going to switch gears again and add more to my design. So in this case, I'm going to start considering my crossing and drainage structures. And just, I'll reiterate it again, especially for the major crossings, sometimes your crossing, or major crossings, oftentimes your crossing is going to dictate where the road should go. So you'll tackle that first rather than after. So I'll add in my crossing structure here. And I'm going to make sure that's sized and positioned appropriately for my environmental and operational requirements. But here, it's a crossing. And if I'm being entirely honest, I don't expect many folks will miss a watercourse crossing in their road plan. Where that becomes more likely is when we deal with those drainage structures. And as Jeremy said, those drainage structures are critical to help reduce how we interact with the surrounding terrain. So we want to add drainage structures, as Jeremy said, to preserve natural drainage flats. So not necessarily where there's a stream, but just where water is naturally being directed towards. We'll also want to add cross drains anywhere we have a low point where water is going to pool against our road. And more so if that water could pool against the road and overtop the road if we had enough water. So that'll wash out your road. But then if we have long segments in between those culverts, we still want to add more pipes than just that. And that is we're intercepting the flow from those cut slopes outside of the actual drainage paths. And we don't want to accumulate so much flow there that we concentrate it, it builds up energy and causes us erosion issues in our ditch or wherever we discharge it. So in this example, I've got the gnarly stuff done. Please don't think that just because we're done the steep stuff, put a straight line to the polygon that we brought in and bingo bango. Flat terrain has its own set of challenges. Usually the biggest challenge is going to be managing drainage. So usually my go-to strategy for that is, well, let's ride the ridges as best we can. So I've exaggerated my scale in my 3D view to see what's going on. And with that, it has a bunch of benefits. So if we're on the ridge, the water naturally wants to go away from our road on either side. We get fewer culverts, which saves us money. It also has benefits from an environmental standpoint. So we're not intercepting as much flow and concentrating as much flow. We're just putting a cap right on top of that hill, and it can go either side. And then from a less drainage specific standpoint, but still related, usually those ridges are going to be better material. So it's going to be better material, better drained. It's going to be easier to construct the road, and you're going to be constructing it with better material without having to import that material. Usually with the flatter designs, the figuring out your horizontal is less iterative. But yeah, this idea of just riding the ridge, sometimes it works great, but a lot of the time it just doesn't work. There's some reason that you can't be there, or there's no ridge. We're not going to explore that in this session, but we will talk about those instances in our seminars later. Now with this, I could have done this earlier on, and usually if I'm designing not for a video, I do. I'll keep track of what's going on quantifiably. So right now I've got my ground types open, which has some costing information in that. So I can use our design time costing function to hit recalculate, and I can see in the bottom right panel there, it's telling me it's about $195,000 to build this road based off the geometry and the assumptions I've made for costs. Now you may not want to blindly follow the costing tool, and I suggest you don't. You should understand what's being involved in that if you're using it. But if you want to look at what some of the cost drivers are, we've got our mass haul diagram there. We can also create a data table, which is going to give us a tabular output of whatever I'd like. So in this case, I'm going to create a data table to show me my cut and fill volumes. So of course, if you build a kilometer of road and I build a kilometer of road, it's very likely there's a different amount of effort for those two roads. If I say that I've cut 30,000 cubic meters of material and you've cut 30,000 cubic meters of material, we have something very similar. Now, if I've cut 30,000 cubic meters of material and you cut 10,000 cubic meters of material, I've done 3 times the work. So it's a useful tool to know what you're up against and also to set production goals and targets. Now, this was a desktop exercise so far. If I want to go take that to the field and make sure everything makes sense and walk my alignment, I'll put together a document and I'll save it in a georeference format. So I can go along with the GPS and see where I'm at and collect any notes to augment my data. So we'll do that, pretend that we've gone to the field, taken those notes, then we can come back into the software. We don't have to look at different screens or different devices. We can take those notes as a KML, dump them into a train file, and we can bring that train file back into location, display the labels associated with it, and we can make whatever changes are necessary. So there, we can zoom in, see what we're dealing with, make whatever changes we want to make, and that's that. So assuming we're happy with where things are at, next step would be to finalize the design, change our multi-plot there, so the actual design document to say for construction, and add any construction notes that you'd like to include on it. We can print it to a paper copy, we can print it to PDF, we can export it as an Avenza file if you'd like. But then if you're doing something a little fancier, and it'll depend on what kind of tools you have to pull from, we can also export that for construction staking in a variety of digital formats. Or we could export it tabularly if you're just staking it by hand. So with that, we'll jump out of the video, back into our slideshow here. And there's a couple things that I didn't cover that I should have. So I didn't do something that I really should have, and if it was a real project, I absolutely would have. Is I just pursued one design option. So I just I chose a route, and I tried to refine it the best I could. Oftentimes there's going to be several options that look like they are viable solutions. So if those are really similar, it may make sense to take them fairly far through the design process before deciding which one's better. Design, it takes minimal amount of time compared to actual construction, and it's really easy to do a design and say, oh, well, I guess this one's better, versus going to construction, building part of a road, then saying, yikes, this is harder than I thought, or I didn't expect to encounter that here. Let's abandon this and try again over here. Another thing worth noting, and I'll reiterate it more than anything, I covered a pretty basic workflow that covers most situations. I suspect most of our current users, I likely didn't cover much that you weren't aware of. Oftentimes it's the details that I didn't elaborate on that will take an okay plan and design and make it something that is really robust and balance all those conflicting goals that I mentioned when I first started. So again, this is our introduction. We didn't dive right into the deep end to start, but stay tuned for our future webinars for more information. And let's see here. This was one of 4. Our next installment will discuss initial planning and locating the road. After that, we'll jump into geometric design. So cross-section geometry, materials, movement, etc., drainage elements, and then our unofficial fifth part, communicating your design. I'll just mention here that it's really hard to isolate one aspect of the design without discussing others. So we'll try to minimize any redundancy, but don't be surprised if we talk about something like water management outside of the drainage webinar, or we talk about material performance outside of the geometric design webinar. So with that, I'm done. Sorry again for taking a while, but we'll open it up for questions.
Excellent. Thank you, Matt. Hopefully my audio is working right now and you can hear me. So we're just gonna, turn it over, please. If you've got a minute and have a question you'd like to ask our panelists, you can type it in now. So you can do that up in the GoToWebinar panel section. As well, just a little bit of, I'm gonna call it housekeeping, but I just wanted to thank everyone for sharing our enthusiasm for this topic. This was a record-breaking webinar for us, so much so that we actually had to twice extend our attendee limit within our webinar platform. So thank you to those of you who have stayed up late, to those of you, particularly in New Zealand and Australia, who have gotten up really early. We have over 50 different countries represented today in our webinar attendees. So yes, with that, I'm gonna just see if Brian
Did you hear me briefly? Of course, my audio is
yeah, cut as soon as you started adding others in.
It's my headset. I apologize. I'm not sure if you guys heard me. I said just thank you to everyone for sharing our enthusiasm for this topic. We've got over 50 different countries represented here today in our attendee list. So yeah, really exciting. So thank you to those who stayed up late, to those who have gotten up early. One question, and I answered it first, and I think my audio is gone, so I'll do it again. But that's if there's going to be a recording of this. So yes, this presentation has been recorded. It will be posted in the coming days up onto Softree's YouTube channel, and you can get access to it. So we'll start with some of the questions that are here, and yeah, reminder, open up that panel, go to webinar Q&A panel, you can type your questions. So the first one, it looks like it's going towards Jeremy, and it is actually more of a comment than a question. Your presentation certainly emphasizes a need to initiate deactivation activities. Yeah, post-harvest. I think it's more of just a comment, just calling some attention to deactivation. I don't know if you wanted to give any remarks on that, Jeremy.
I think so. It's not just thinking about the planning and how you're going to deactivate the road, but even if you go back to the planning level of where your road is and how that will impact when you're deactivating, if you have the road in the right place, your deactivation activities may be far reduced. And again, that's for temporary roads. In the life cycle of a permanent road, we won't deactivate. So the more the focus in the life is how we're going to use and maintain it.
Excellent. The next one is actually a software question. So Matt, I'm going to pass it over to you. Is the costing module available in standard Rodent?
Yes, absolutely. So we do have an optimizer as well, which will help kind of turn the vertical alignment design into a semi-automated one. But regardless of whether you have that optimizer, which the costing software pulls from some of the technology in it, that's still available in the standard Rodent package. And I'll just add a comment to Jeremy's and the question about deactivation. I think another thing that often gets overlooked more for the permanent roads, or at least the roads that aren't planned to deactivate, and it might just be an idea that, oh, we'll use it again in 20 years. If you have something that has an obvious maintenance requirement to it, it's important to consider whether that's actually reasonable to commit to the maintenance requirements for it. And that often dictates whether it's something that was going to be a permanent road should maybe be at least partially deactivated as well.
Okay. So, friendly reminder, if you do have questions, this is a remarkably large audience that is very quiet. Please feel free to type them in. I'm not sure, Brian, I know that you've obviously had a large contribution today to the development of the content. I'm not sure if you wanted to share a few remarks from your side.
You know, I think that the presentation, again, it's introductory, but it was intended to really focus the overall planning around thinking about the life cycle context of a road, in that at the front end of the life cycle of a road, when you're planning it, is the best time to minimize its impact. And so, as Jeremy indicated, failure to plan is planning to fail. Wasn't there a slide for resources as well?
There was, and I've moved it. Yes, we will be sharing the resources as well as actually a PDF presentation, a PDF of this presentation, I'd say, along with our follow-up note. So you'll get access to a list of resources as well as our presentation and the video recording as a follow-up. Awesome. There are a couple more questions, and just a reminder, given the large number of folks that are attending today's webinar, your mics are actually going to stay muted. So if you'd like to ask a question, yeah, please do type it into that Q&A section. So the next question here, I think this one's coming to you again, Jeremy. Which would be the best deactivation method to minimize overhunting an area?
Well, we've been involved in a few different barrier jobs over the years, and we have not had a successful one yet. We were very close. We had a lock block wall where we pinned the lock blocks together, and it had a fall down the other side, and it just took them a little bit longer to get by. So it's really hard to keep quadders out of the area. But the hunting thing, there's a couple of other things even before that. You know, long straightaways are real good shooting corridors. So even at the planning stages, if you want to avoid those long straightaways, you can shorten the sight lines for hunters. But you know, tank trap cross drains will keep all the big vehicles out, and at least it'll just be the not faint of heart that get in. But everything from gates to rock piles, they all get plowed over or diverted around. The most accessible gates are the ones with the heavy guarding on the internal locks, and placed at places in the road where it's not easy to get around them. But even those now with the cordless zip cutters, it's really difficult.
Awesome.
Trying to block access is a significant issue in BC. There are people that actually go out there with the intent to find them, with the intent to breach them as a challenge. For temporary barriers, it's really difficult. But if you're trying to permanently impede vehicles from traveling on a road, you really need to destroy the front end of the road so it can't be used. Then with regard to Jeremy's comment about minimizing sightlines for hunters and shooting, it's a really good idea if you've got a main access road and you've got straightaways off of that to put a dog leg in off of your secondary accesses so you can't see from your main line as you're driving down it straight sight lines down the secondary accesses.
Yeah, and obviously full recontour debuilding of the road is the only way to stop vehicles from coming in. But like Brian said, that can be just the first couple hundred meters as well.
Okay. Lots of extra comments coming in tied into some of the subject matter. I think this is just trying to go through them. There's so many. So we have, this is just more of a comment, I guess. We have some large scale road restoration projects within British Columbia, tearing up compacting surfaces and promoting vegetation growth. So thank you for that comment. As well as a couple other comments with regards to the overpredation, as well as with wolves. So a curvilinear alignment can help against overpredation from wolves and other animal predators too, not just humans. Thank you for that. And very similarly, in Alberta, we had to do dog legs every 400 meters for that purpose to prevent wolves from overtaking animals. So yeah, very.
The other piece to that debuilding comment is when you're decompacting the soil or spreading vegetation to promote vegetation growth on the road, it's really important to consider not only the surface but the subsurface. So when you're debuilding a road, the first thing that you need to do is debuild or not the first thing. Important thing to do is to debuild that road prism underneath. So and it's sometimes impossible to. If you have a road and rock cut, you can't debuild that rock cut. And so you can have subsurface water still hit that road under the ground and flow along the road and come out somewhere where you don't expect. But if you're in sufficient materials, you debuild that road underneath. So when you decompact, you're decompacting a surface that's sloping across the road, not down the road, or sloping more across than it is down. So you're still promoting water to disperse evenly down the slope and not catching subsurface water and diverting it on some hardened surface under the ground.
Yeah, just to add to that, when you're doing deactivation work, you want to really explore what the natural drainage patterns were before the road. And then you want to try and reestablish those as best you can. And with regard to the comments that Jeremy's making, with the road surface, it's really difficult to decompact them. Yeah, you should make efforts to do that. But when you're doing the deactivation, one of the ways to think about it is if the water goes onto the road surface, what can I do to get the water across the road surface quickly? So even though you're decompacting the road surface, you might actually put in cross drains, which you'll actually end up burying anyway in key areas in order to carry the water that's likely to hit an impenetrable layer, i.e. the old road surface.
Excellent. A question for you, Jeremy. What has the trend of pitching maintenance items, for instance, culverts, been like to stakeholders in your career? And how do you predict what will be like for the next generation of consultants? Not a small question.
Yeah. I think it depends on the client and how long they're there. One of the things I think, especially when you're talking to road builders about how they're building road, a lot of them never get to see their structure, or they don't go see their structure over time. And they'll tell you, well, I can put that fill there. I've never killed a logger, or, I've never had a machine fall off. That doesn't mean that over time, you're still not going to have instability. And in the same way with drainage structures, as long as it made it through the service life, the temporary service life that manager was talking about, then they don't care. But I found it's a lot easier, certainly for main lines, because as soon as it's easy to see that drainage is causing an issue to the road, and that's almost always what happens. If you don't have adequate drainage structures, you're going to get erosion of a ditch or into the road prism, or an unstable fill slope where you've had water going over. Those things are real. So those are fairly easy to understand. I think one of the things that I do when I talk to folks about minimum culvert sizes now is that in the resource sector in general, and actually, you know, across a lot of the sectors that we work in, and even into highways, maintenance of drainage structures is often an issue. So in a resource road, we don't size the cross drain culverts for flows only, because if we did that, a lot of our drainage structures could probably be, you know, 6-inch pipes. But that's not what happens. What happens is something gets at the inlet, a stick, a twig, a little bed load wedge, and those are the things that impact the size. And so when folks kind of think about that, and then you go out and look in the field and go, oh yeah, well, I'm using 600 millimeter diameter pipes just for my cross drains, but I go in the field and every one of them is half full. That's the reason they're that big. So I think the more we talk about it, the better. And of course, it's easy with main lines. It's hard on stuff that's temporary but stays in place that folks just aren't looking at.
Muted again. With that, I think I'm actually going to wrap up today's presentation. Thank you, Jeremy, Brian, Matt, for your content. I hope you have all found this extremely valuable. This was, as we've said a couple of times now, this was part one. This was the foundational layer. And we really look forward to sharing a whole bunch more content in the subsequent 3 webinars on more details on how you can reduce the environmental impact of your roads through planning and design. So this will be posted up to our YouTube page, and we look forward to seeing you all again at the same time and the same place, pretty much for part 2 coming up in 2 weeks. So have a wonderful rest of your day, and look forward to seeing you all again soon. And for those of you, I should say, who have asked a whole bunch of software-specific comments, we're actually holding them. We will reply to you over email, because this is not about RoadEng so much as it is about the impacts and considerations that you need to have. So we will follow up with you individually. Have a wonderful day, everybody.